Google can now keep an AI agent working after your app disconnects, give it a remote computer, and connect it to outside tools through MCP. Under this architecture, the model operates as a managed worker. In a standard setup, if the connection between your application and the server drops, the task fails. A timeout occurs, the process stops. Now, when that connection is severed, the cloud environment assumes responsibility for the task and continues the execution. While your application is offline, the agent continues its work in the background. It executes code, manages internal files, and conducts research, operating independently within its own persistent state. The cloud acts as an asynchronous digital worker, holding the state of its task until the job is complete. Previously, building this kind of system required writing complex while loops to manage the agent's reasoning. Developers had to provision and maintain their own local sandboxes, which often proved fragile under production workloads. This raises a question for developers. What changes when you stop managing those execution loops and hand the entire runtime over to Google's infrastructure? Making that transition involves surrendering granular control over the execution environment. In exchange, you gain the ability to scale these operations without managing the underlying hardware. Trading local control for cloud infrastructure shifts the developer's role from writing execution loops to governing agent behavior. Managed agents in the Gemini API operate inside a secure Google-hosted Linux environment, isolated at the operating system level. The API handles internal reasoning, tool selection, and package installations. It maintains a local directory, preventing the need to pass heavy payloads over the network. Because the sandbox manages its own setup and maintenance, developers can focus entirely on defining the logic of the task rather than infrastructure maintenance. These long-running tasks operate invisibly using background execution. You can trigger an agent to work on a heavy process and, if needed, issue a specific API command to cancel the operation before it finishes. To interact with external data, the agent relies on tool gateways. Through these gateways, the agent can execute code, query Google Search, call custom functions, and connect to remote MCP servers. Tokens are injected securely via header transformations and refreshed across interactions, ensuring raw credentials are never exposed inside the sandbox. Providing tools without handing over the base credentials builds a necessary firewall. The agent gets the operational capability it needs, while your core systems remain protected. All of these capabilities are routed through the Interactions API. This single endpoint acts as the unified interface for calling standard Gemini models and managing these complex autonomous agents. It uses server-side state management. By passing a previous interaction ID, the server recalls the entire conversation history, which improves cache hit rates and reduces overall token costs. This architecture also provides real-time observability. You can monitor the exact sequence of execution steps, tracking the model's internal thoughts, its specific tool calls, and the final generated output. Since cloud-hosted execution is otherwise opaque, this unified API glass is the primary way developers maintain trust and visibility into the agent's logic. Relying on this managed infrastructure introduces a clear trade-off. You are now reliant on the platform's security behavior and permission structures to protect your workflows. The sandbox presents a security paradox. It is isolated at the OS level, yet by default it is configured with unrestricted outbound network access. This places the responsibility on the developer. Before deployment, you must build strict network allow lists and implement least privilege service accounts to restrict where the agent can send data. To prevent infinite processes from draining resources, there is a hard lifecycle limitation. If an environment sees 7 days of inactivity, it is systematically deleted. Autonomous capability needs strict boundary constraints, making network governance the most critical phase of agent deployment. There is also a financial reality to this architecture. Because a single user interaction triggers multiple hidden reasoning loops in the background, token costs scale rapidly. A managed agent interaction typically consumes between 100,000 and 3 million tokens to complete its task. During the preview period, the compute required to run the environment itself is not billed. This makes tool usage and raw token consumption the primary economic factors to monitor. The next agent platform won't win only by reasoning better. It will win by making long-running digital work observable, governable, and cheap enough to trust. True scalability in the AI era relies on the economic and infrastructural guardrails that surround raw intelligence.